Okay. So now we just want to see for all m and m. And so we have this statement, this is P of n. We're proving P of n by induction. So far, we've proved m for all m. Okay, so our induction hypothesis is to assume P of n for some natural number n. So let's do that. So induction hypothesis, or IH, assume P of n for some n. That is, assume for all m plus n equals. Okay. And now we want to show our, I guess as an aside, our goal is to show that for all m plus n plus 1 equals n plus 1 plus m. That's what we have to do in the induction step. Our tools, well, we have to use the induction hypothesis. We have to use the definition of addition, the definition of addition. So we need to use induction in the induction step, just like we needed to use induction in the base case. That's okay. So induction step. Okay. So so I've used P and Q, so let's do R. R of M just be the statement that n plus 1 equals n plus 1 plus m. We want to show R of M by induction. We have to prove R of M by induction. So that means we need to do the base case, induction hypothesis, and induction step inside this one induction step. Okay. So base case for R. R of 0 is just a statement that 0 plus n plus 1 equals n plus 1 plus 0. Okay. This is actually something we've already considered in the base case of an induction for P. So already done. In P of 0. Okay. At least we saved ourselves some work there. Okay, now assume induction hypothesis, assume R of m, that is, assume m plus n plus 1 equals n plus 1 plus m. And we need to show, our induction step, we need to show m plus 1 plus n plus 1 equals n plus 1 plus m plus 1. If we do this, then we can conclude that finishes off the proof that Rm plus 1 holds. By induction, we have shown that Rm holds for all m, and that shows this induction step, which is that shows P of n plus 1. Then by induction, we conclude P of n for all n, and that's what we want. Okay, so this is kind of like the main step in this induction step in this part of the in this induction is kind of like the main part we have to work on. The rest of it so far wasn't too bad, I guess. Okay, so we have to show this, and what we know is that we know m plus n plus 1 equals n plus 1 plus m. We know P of n, so we know for all m plus n equals n plus m. And hopefully that's enough. Okay, so Let me write, so yeah, we want to show this. Let me write down all the things we know. We know, I'll rewrite our induction hypothesis for P using K instead of M. So we know that K plus N equals N plus K for all K. Let's see, what else do we know? We know that N plus 1 equals N plus 1 plus M. Okay. So let's start from this side and see what happens. See if we can kind of do it step by step. First, we start with M plus 1 plus N plus 1. Well, the definition of addition, this is an N. The definition of addition says that you just add M plus 1 plus N and then add 1 to that result. So I'll put, oops. Okay. That's the definition of addition. Okay. Now we know for all K that K plus N equals N plus K. So this is really the same as N plus M plus 1 plus 1. That's by induction, by the statement of P of N. Okay. Now I want to change, I want to make this, somehow I want to make this N plus 1 plus M. Okay. And I do have, so if I'm able to get to this point, N plus 1 plus M, then I can use induction, the induction step, the induction hypothesis for R to say that N plus 1 plus M is just M plus N plus 1. Oh, sorry, I want to transform this into this, and then I can transform this into what I want, which is N plus 1 plus M plus 1. Okay, yes, that's my plan. Okay, so for my next goal is to get here. Okay, so how do we get there? Well, luckily, we can use the definition of addition again. This is N plus something plus 1, so we can remove the plus 1. So again, we get what? So this is just N plus M plus 1, and then add 1 to that. That's the definition of addition. Now I can use induction, the P of N again, to say that N plus M is M plus N. That's by P of N. Okay. And the definition of addition says that this is just M plus N plus 1. Okay. Now the induction hypothesis R says that M plus N plus 1 is just N plus 1 plus M. Oh yeah, so this is definition of addition. This would be N plus 1 plus M plus 1. That's the induction hypothesis R of M. And now this is just the final step is to say that this is just N plus 1 plus M plus 1 by the definition of addition. And where did we start? We started with M plus 1 and N plus 1 in the other, like in the other way around. Okay, so we've shown R of M plus 1. So that kind of concludes this. So see this induction, which we started over here? That induction is done. Okay, so let's see what it says. So that concludes, so R of M plus 1 holds. Therefore, R of M holds for all M. And what did R of M say? It just says that M plus N plus 1 equals N plus 1 plus M. So that holds for all M. And therefore, that's just P of N plus 1. So this was like by the middle inner induction. But now our conclusion, it says that by induction, P of N holds for all N. So N plus M equals M plus N for all M and N. Okay. Okay. Okay, so now you can, now you really know, I mean, how we usually explain this is that, like, if you have 5 apples and 3 apples, that's the same as 3 apples and 5 apples. Okay, sorry, 5 and 3. 5 and 3 is 3 and 5. Yeah, but now you can kind of reassure yourself that it is also, you can prove it too. Okay. Of course, you can imagine if you had to prove the associative law, that would be using like 3 inductions. Obviously, that's going to be a lot more tedious. But although it's going to like take a lot more time, it's not any more difficult, it's just the same, you're doing the same stuff as you did for this. I guess there's like, you just have to keep track of everything very carefully. Okay. Okay. So let me put that as an exercise. You can try to prove that m plus n plus k equals m plus n plus k. Actually, it might not be so bad, but try it anyways if you want or don't. Okay, you can try to show that if m is less than n, then m plus k is less than n plus k. You can also show that if m is less than n, then there exists k with n equals m plus k. In other words, this allows you to subtract. This allows you to define like n minus k or n minus m. You have n minus m equals k is what that lets you do. Or you could, prove any arithmetic thing you want, right? Another exercise is to define multiplication using the recursion theorem and prove something like m times n equals n times m. Of course, when you prove m times n equals n times m, you might have to use like some property of addition, which you can take as given. Okay, and of course you could do this for any of your favorite. There's so many. I won't write them. You could prove associativity of multiplication. You could prove the distributive law. You could prove something involving multiplication and inequalities, whatever. Okay. And then you could also define exponentiation. You could prove like the laws of exponentiation and everything like that. Okay. Okay. So, I might put one or two of these on an assignment. Once they're not once it, at least some of the simpler ones, Okay. That is as far as the natural numbers goes. We're gonna stop there. We might do a couple more examples on Wednesday. And then next up would be the real numbers. The reason why we skip from the natural numbers to the real numbers is because, well, like traditionally constructing the integers and the rational numbers, that's kind of like left to the realm of algebra. Okay, we could do it. It's just stuff with like with equivalence relations, and maybe I'll sketch it quickly, but mostly we're just gonna skip straight to the real numbers. Okay. Okay, so anyways, that's all I wanted to say to you guys today. If you're still, watching, thank you. Or if you're gonna watch on YouTube later, that's great too. Okay. Well, I see there's a chat. I hope it hasn't been there for long. Oh yes, okay, yes. Take care. Bye.